Section 6.8 is the second of 3 consecutive word problem sections. I don't think I've ever asked a question from section 6.9 on the test. I ask you to do 6.9 if you want to use a note card on the test, but other than that, you don't have to worry so much about section 6.9. There's guaranteed to be at least one problem from section 6.8 on the test, and I'll just kind of jump into problem 2, and then I'll flash problem 1 back up on the screen. If you lay my problem 2 on top of your problem 1, you'll see that they're essentially the same problem, just with slightly different numbers. So for both of our problems, there's a sentence or something that's that describes a formula. It says the number of people who have heard a rumor can be modeled by the function n of d equals 5 times e to the 0.25d, where d is in between 0 and 20. Then it says n of d is the number of people that have heard the rumor after d days. So in the formula, the left-hand side, the n of d, this represents the number of people that have heard the rumor. So that's what the left-hand side represents. And the D represents the number of days. I guess the number of days since the rumor had started, I guess, might be a nicer way to say that. And this little parenthetical comment, which I was missing a left parentheses, that my D is in between 0 and 20, says that this formula is only valid for the first 20 days of the rumor, and then after that the formula is invalid and it won't be useful in predicting the number of people that know the rumor. So part A of question 2 as well as part A of question 1 just wants me to get used to understanding the function essentially. And it says determine the number of people who have heard the rumor after 5 days. This question, or the sentence, has a number in it, and that number stands for the number of days. To get the answer, the number of people that have heard the rumor after 5 days, that's the n of d, I'm going to just plug 5 in for d, and I would read this as the number of people that have heard the rumor after 5 days equals 5 times e to the 0.25 times 5 power. So all I'm doing is I'm taking the number of days and plugging it in on either side of the equal sign for the d. So I would read this as the number of people that have heard the rumor after 5 days is 5 times e to the 0.25 times 5 power. And I'm just going to figure out what this is on my calculator. And you can't have a fraction person, so I'm going to round it to the nearest person. So on my calculator, I'm just going to go 5. And then I'm going to hit second and ln, and then I'm going to type in 0.25 times 5 and close the parentheses that my calculator started. And this is 17.45 people. I'm going to round that to 17 because it says round to the nearest person, and I'm not going to round up to 18 because 0.45 is less than 0.5. So I'm just going to say 17 people. If I want to, I can say 17 people have heard the rumor after 5 days. 17 people is sufficient for an answer. But if you want more, you can give me more. The function that's given here is a little bit like the a equals p e to the rt function. In fact, it's a lot like that function, except it doesn't have the same letters. But it's an exponential growth function. And when it asks me for the growth rate, when we did the questions in the last section, the interest rate we shoved into the exponent. That interest rate position is going to be the growth rate's position, and in this particular problem, this 0.25 is going to be considered the growth rate, and as a decimal, the growth rate is 0.25. Usually, when we're asking for growth rates, we usually change the decimal back into a percent. So I'm going to take the decimal and move it 2 to the right, and I'm going to say the growth rate is 25%. And then part C, how many days will it take to 100 people have heard the rumor? Well, the number that's given in this problem, this question is 100, and the number of people that have heard the rumor, that's what the variable to the left of the equal sign represents. So to answer this question, I'm going to take the 100 and plug it in for the n of d, which is the number of people that have heard the rumor. And I'm going to solve it for d. D is the number of days. I'm trying to find how many days. It means I'm solving for d. And this is going to take a few steps to solve. It's just like the steps that we used to solve the problems in section 6.7. I'm going to start off dividing both sides by 5. And I'll go this way because I'm kind of out of room here. This is going to give me 20 on the left side. And it's going to give me equals e to the 0.25d on the right side. Now I'm going to take the natural log of both sides. That's going to give me the natural log of 20 equals 0.25d times the natural log of e. And that natural log of e is still equal to 1. If I do natural log of e using second and divide to get the e, you get the natural log of e is 1. So this is really the natural log of 20 equals 0.25d times 1, which is just the natural log of 20 equals 0.25d. I'm trying to solve for d, which is the number of days it'll take for 100 people to hear the rumor. And I'm going to divide both sides by 0.25. I'm going to pull out my calculator. And on my calculator, I'm going to type ln of 20. And then I'm going to hit the divide key and divide it by 0.25. And that's going to give me the number of days because it's going to solve me for d. So when I do this, I'm going to get d on the right side when I divide. And on the left side, I'm going to get something that I'm going to use for my answer. So natural log of 20 divided by 0.25. And I get 11.98. It says 11.98 days. The instructions say to round to the nearest day. So my answer for part C is that it's going to take about 12 days for 100 people to hear the rumor. I don't have enough room to write it's going to take 12 days for 100 people to hear the rumor. And this is a completely adequate answer. Really, the 12 days is the most important part. When you go to do problem 1, it's exactly the same kind of problem. I give you essentially the same formula with slightly different numbers. The left-hand side represents the number of people who have heard the rumor after d days. The right-hand side is the d days, and it says this formula is only good between 0 and 30 days. Once we get beyond a month, this formula won't be useful. And so the parts of yours is just like the parts of mine. So if you reflect back to my parts A, B, and C, if you don't know how to do this immediately, that should push you through and get you started with this. Our problems 3 and 4 are clones of each other for what that's worth. If you look at your problem 3 and my problem 4, if you lay them on top of each other, they're essentially the same question. So it says the size, P of t, of a certain insect population in time t in days obeys the model P of t equals 500 times e to the 0.06t. Your question or your statement is exactly the same, except the formula is just tweaked a little bit. So when we go to answer the questions, the algebra that I do should be just like the algebra that you do because the question's essentially the same. So I need to understand in this problem that the variable to the left of the equal sign is the size of an insect population. I guess that probably means the number of insects in this particular population. So I'm just going to say it's the size or the number of insects. And the t on the right-hand side represents the number of days. When I go to do part A, it says determine the number of insects at t equals 0 days, and then it says we call this the initial population or the starting population. What I'm going to do is take that 0 and plug it into the formula for t. So I'm going to get p of 0, the number of insects after 0 days, equals 500 times e to the 0.06 times 0. I know that equals to 500, but I'll do this on my calculator if you don't believe me. So I can go 500 and then second in ln to get the e, and then 0.06 times 0. And it's going to give me 500 back, because this is really 500 times e to the 0, because that exponent multiplies to be 0. Anything to the 0 power is 1. So this is 500 times 1, which is 500. So at 0 days, or right when we start observing this insect population, there are 500 insects. So there are 500 or whatever these insects are. I could say at day 0 or at the beginning of this study, but it says 0 days, so I'll stay day 0. That's a nice answer. If you just said 500 insects, that would be probably, if this was a test question, what I would be, writing on my key. What is the growth rate for the number of insects? For these exponential functions, the growth rate is the decimal next to the letter in the exponent here. So the growth rate as a decimal is 0.06. I'm going to move that decimal over twice to make this into a percent and get 6%. And I'm going to write the growth rate for this insect population is 6%. Part C, what will the population be after 9 days? That's not a completely different question than part A. I'm just going to plug in 9 for D and get the insect population. So I'm going to do P of 9, plugging in 9 for that T, and then plug in 9 for that T, equals 500 times e to the 0.06 times 9. And I'm going to round to the nearest insect because can't have a fraction insect. So on my calculator, I'm just going to go 500 second in ln 0.06 times 9, close out the parentheses, and I'm going to round that to 858. And I could write a sentence and say after 9 days there'll be 858 insects, or I could be lazy and this would be completely adequate for an answer saying there's 858 insects. Again, you could write there will be 858 insects after 9 days if you want a better answer than what I have in my box. But it's not necessary. Just that number box is completely fine. When will the population reach 10,000 insects? I need extra paper for this. I've got to dig some out. All right. So in part D, the number that they give me represents the number of insects, and that's what the left-hand side of the equation stands for. So when I'm going to go to do part D, I'm going to solve for T, the number of days, and I'm going to plug in 10,000 for the number of insects. So on the left-hand side of my equation, I'm going to plug in 10,000, and I'm going to leave the right side 500 times e to the 0.06t. And I'm going to solve this for t, which is the number of days, or the time in days. To do this, I'm going to divide both sides by 500. That's going to give me on the right side 20. On the left side 20, and on the right side e to the 0.06t. Then I'm going to take the natural log of both sides. I'm going to leave the left side the natural log of 20. The right hand side I'm going to make it 0.06t times the natural log of E, which is going to be 0.06t times 1, because the natural log of E is 1. So I can rewrite the right-hand side as just 0.06t. The left-hand side is the natural log of 20. I'm going to divide both sides by 0.06. On the right-hand side, that's going to give me a t. And on the left-hand side, I'm going to use my calculator. It's going to give me the answer, and I'm supposed to round to 2 decimals. So I'm going to get whatever that number is and round it to 2 decimals. So I'm going to do the natural log of 20 divided by 0.06, and I get 49.928. This 2, you're either going to leave a 2 or round up to a 3. Because the number after it's an 8, I'm going to round it up to a 3. And I'm going to write 49.93. That's the numerical answer for part D. I should at least give a word with that so I understand that that represents the number of days that it's going to take to get 10,000 insects. And when I go to write my answer for part D, the least you can write is just like 49.93 days. That's what I'd probably write on my test key if this was a test question. But if you want more words, you can say it will take 49.93 days for the population to reach 10,000 of whatever these insects are. I don't do sentence answers unless somebody really forces it to me. Okay, part E, how long will it take the population to triple? Well, the population started off at 500 insects. Tripling 500 is multiplying 500 by 3. So this is asking me how long will it take for the population to reach 1,500 insects. And I'm going to do that just like part D. Part D, I found out it took just about 50 days to reach 10,000 insects. Part E, I'm going to do the same sort of computation to figure out how many days it's going to take to get to 1,500 insects, which is tripling the initial population. So for part E, I'm just going to go 1,500 and put it on the left-hand side for the future population equals the formula 500 e to the 0.06t. And then I'll do the algebra. I'll divide both sides by 500. That's going to give me 3 equals e to the 0.06t. Then I'll take the natural log of both sides. I'll get the natural log of 3 equals 0.06t times the natural log of e. The natural log of e is 1, so this really gives me the natural log of 3 equals 0.06t. And then I'll divide both sides by 0.06. I'm supposed to round to 2 decimals again, so on my calculator, when I do the natural log of 3 divided by 0.06, I get 18.31 for t. And for an answer, it's going to take 18.31 days for the population to triple. For an answer, I would probably just write 18.31 days. But you certainly could write words. You can say it will take 18.31 days for the number of insects to triple, if you care to write a sentence. So that's everything for problem 4. I'm going to flash up your problem 3 so you can pause the video and give it a go. Again, it's basically the same questions. And now we can flip on to 5 and 6. And 5 and 6 are similar problems. I kind of like my 6 better than your 5, but they're similar. Your problem 5 talks about a radioactive material, and it gives me a function that tells me how that, I don't know exactly what to call that, element decays, I guess, could be a compound. Anyways, your problem gives me a substance, and a formula about how it decays. So radioactive material breaks down, it's not stable, and over time, if you start off with a pile of it, over time it's going to break down and you'll have less of it. For my problem 6, if you drink a Starbucks or something in the morning, you get a caffeine spike, and that caffeine slowly leaves your body. If you're addicted to caffeine, as it leaves your body, you start getting a headache. And this formula gives me, in this problem, caffeine leaves the body according to the function P of t equals P sub 0 times e to the negative 0.139t, where P of 0 is the initial amount of caffeine present. So in this formula for my problem 6, P sub 0 is the starting amount of caffeine in your body. So P of 0 is the initial amount present, and P of t is the amount after t hours. So the P of t is the amount of caffeine in your bloodstream or in your body after t hours, and it goes down. If you're not replenishing your caffeine, it's going to be it just decays or gets used up, gets absorbed into your body, I imagine. So the variable here is the amount of caffeine starts in your body. This variable is how much is left in your body. And the T is for time in hours. So the T is the number of hours after you've drank or ingested the caffeine. All right. Well, assume that a person has just consumed 100 grams of caffeine. That's probably just like a Starbucks. I think that's all that is. What is the decay rate? You'll notice the exponent in this problem has a negative. And in these exponential functions, if the exponent is positive, then the amounts are going to get bigger, like the number of insects kept getting bigger. Here, it has a negative exponent, so the amount of caffeine in my body or your body's going to go down. The decay rate is this negative 0.139 or the negative 0.139. And the negative means the amount of caffeine in my body is going down. And as a percent, it's going to be negative 13.9%. The negative means the amount of caffeine in your body is going to go down. And you can include that negative in the parenthesis in your answer, but you don't really have to. You can just say 13.9% is the decay rate, because the word decay implies to me that the amount is going down as opposed to going up. Growth rate means the amount would be going up. Decay rate means the amount is going down. So when you go to do your problem 5A, it says what is the decay rate of Krypton 85? You'll look at your formula. Your formula has a negative in the exponent, which means the amount of the material is going to be going down as opposed to going up. And the decay rate is that as a percent. How much caffeine will be left after 21 hours? I know that this tells me to plug in T for 21 because that's what the T represents the number of hours. So into this formula, I want to find out how much caffeine is left, and it means I'm solving for P of T. That's the amount of caffeine that's left in your body. Into the formula, I'm going to plug in 21 for T, and I'm also going to plug in 100 for P sub 0. That's the starting amount of caffeine that's kind of buried in this problem. So what I'm going to do is put in a 21 for that P and write P of 21, the amount of caffeine in the body after 21 hours, equals 100, the starting amount of caffeine that was given in this problem, times e to the negative 0.139, just putting 100 in for the starting amount of caffeine, negative 0.139 from the formula, and in for T, I'm going to put 21. This is going to be just something I'm going to do on my calculator. And this is going to be how many grams are left, because the caffeine is in grams. So that's a lot of, maybe it's supposed to be milligrams. 100 grams might be, gosh, that's like 30 ounces of caffeine. That might actually kill you. This is probably supposed to be milligrams, but I'm not a chemist or a scientist, so my units are a little maybe suspect here. Well, that's 3 ounces. That's a lot of caffeine. So I'm just going to go 100 times second ln negative 0.139 times 21, close out my parentheses, and this gives me 5.398, and that's a bad number for rounding purposes. So this 5.398, if I'm rounding it to 2 decimals, this 8's going to round that 9 up to a 10, and that 10's going to round the 3 up to a 4, and there's going to be 5.4, so it's mostly gone, 5.40 grams left after 21 hours. So most of it has left your body, and that's why you start getting a headache. I could write there'd be 5.40 grams left after 21 hours, but I don't have to. So for your part B, how much krypton will be left after 30 hours? Well, into your formula, you're going to plug in 30 for those T's, and in for the P sub 0, you're going to plug in 1,000. So you're going to go P of 30 for 30 years equals 1,000, because the initial starting amount of this krypton is 1,000 grams, times e to the negative 0.063 times 30. All right. Part C, when will 10 grams of caffeine be left? Well, I want to solve for the number of days that will have 10 grams left, and that's 10 is going to go on the left-hand side because it represents the amount left in my body. So to do this part C, I'm going to put 10 equals the starting amount of caffeine, which is 100, times e to the negative 0.139 times t. And after 21 hours, I have 5.4 grams left. It has to be less than 21 hours because this is more than 5.4 grams. So I'm just going to solve this for t to get the number of hours that it's going to take for it to be 10 grams left. So I'm going to divide both sides by 100. And on the left side, I'm going to write this as a decimal. It's going to give me 0.1 equals e to the negative 0.139 t. And then I'm going to take the natural log of both sides. On the left-hand side, I'm going to make it the natural log of 0.1. On the right-hand side, I get negative 0.139 t times the natural log of e. The natural log of e is 1, so I can write this as the natural log of 0.1 equals negative 0.139 t. And then I'll divide both sides by negative 0.139. On the right-hand side, I'll get the value of t that I'm solving for. And on the left-hand side, when I do the natural log of 0.1 divided by negative 0.139, I get the number of days. And I believe it says round to 2 decimals, so this is 16.565. I'm going to round that up to a 7. That's hours, I should say, if I might have just said days. So after 16.57 hours, that 100 grams of caffeine will have broken down into 10 grams of caffeine. After 21 hours, that 100 grams broke down to 5.4 grams. So when I go to write my answer here, I'm going to say it's going to be 16.57 hours for there to be 10 grams left. When you go to do part C of your problem, when will 200 grams of Krypton 85 be left? You're going to plug 200 in on the left-hand side. 200 and not 2,000. The right-hand side, you started off with 1,000. And you're going to solve that formula for T. D's a little tricky. D asks me, what is the half-life? The half-life is the amount of time it takes for half of the initial amount to go away. So for me, I started with 100 grams. The half-life is the time it takes for there to go down to 50 grams. And to get the half-life, I'm going to plug in 50 grams for the future amount of caffeine equals to the 100 grams, which is the starting amount of caffeine, times e to the negative 0.139 t. The half-life is the amount of time it takes for half of the drug or whatever is decaying to be left. Solve this. I'm going to divide both sides by 100. This is going to give me 0.5 equals e to the negative 0.139t. I'm going to take the natural log of both sides. This is going to give me the natural log of 0.5 equals negative 0.139t, natural log of e. Natural log of e is equal to 1. I'm going to divide both sides by negative 0.139. The right-hand side is going to give me a t. The left-hand side, I'm going to use my calculator and round to 2 decimals. So I'll do the natural log of 0.5 divided by negative 0.139. And I get 4.986. I'm going to round that to 4.99. So this says in about 5 hours, half the caffeine that got into your bloodstream will be out of your bloodstream. So the half-life of caffeine is 4.99 hours, which is about 5 hours. I've always thought the half-life of caffeine was about 6 hours, but this is probably more accurate. I'm sure I stole that formula from someplace I found online. For your part D, to find the half-life of Krypton 85, we're starting with 1,000 grams. You want to find out how long it takes to go down to 500 grams, so you're going to put 500 in for the left-hand side of the equation. On the right-hand side of the equation, you have the initial amount of 1,000, and you have the negative 0.063 t, and you're going to solve that for t to get its half-life. So the word problems in the rest of the section are kind of quite a bit more difficult. If you glance at them, they may not look that hard. For the next problem 7 through 10, we're going to use this exponential growth formula that we've been using, where the left-hand side is kind of the future population. The first number, the p sub 0, is the starting population. The k is the growth rate. The t is the time in hours or maybe days or maybe years. And if I look at your problem 7, talks about the rodent population in a given city that rose from 20,000 to 30,000 in 1 year. And then it says, how long will it take the population to reach 100,000? So it's just a short question. Doesn't look that imposing. It turns out that it is pretty tricky to do. And I will do my problem 8. And as I do my problem 8, I'll walk you through problem 7. My problem 8 says the bacteria in a laboratory culture increased from initial population of 500 to 1,500 in 3 hours. That's like your rodent population going from 20 to 30,000 in 1 year. And then how long will it take the population to reach 10,000? There's the next. That's right. How long will it take the population to reach 10,000? How long will it take your population to reach 100,000? So they're really similar questions. They're written properly, but they're written in such a way that it's going to be deceptive to know what to do. So as I go through to do my problem 8, I'm going to break it up. And specifically, I'm breaking off the top 2 sentences from the bottom sentence. And when I go to do your help you get started on your problem 7, I'm going to break up the top sentence from the bottom sentence. And so if you look at what I have written on this next page, what I've done is I've taken my top sentence in chapter and for problem 8 and separated and made a big gap to the bottom sentence. When I flash up your problem 7 again, I'll have taken this top sentence and made a big gap, and then I wrote the bottom sentence. So I'm separating the sentences here because they kind of need to be separated. So in problem 8, this is a 2-stage problem. I'm going to use the information in the first sentence to tell me how fast in terms of the growth rate this bacteria culture is growing. In all the problems that we've done so far, problems 1 through 6, the formula either had a growth rate in it, I think the formulas had a growth rate in it. In this particular problem, 7, 8, 9, and 10, I'm given information that's going to help me compute the growth rate. So for problem 7 and problem 8, I'm going to use the numbers in the first sentence to compute or solve for k. Super easy to do because we know how to do this. This number 500 is going to go in for the starting population, and so I'm going to put that in for p sub 0. This number 1500 is going to go in for the future population. I'm going to put it in for the p of t. Actually, it's going to be a p of 3 that I'd put it in for. And the 3 is a number of hours. I'm going to plug that in for t. So into my formula, I'm going to plug in p of t, which is really going to be p of 3. I'm going to plug 1500 in. I'm going to plug p sub 0 equal to 500 and t equal to 3, and I'm going to use that and solve for k, and I'm going to round k. I should have said this in the instructions. On the test I do. I'm going to round k to 3 decimals. K is probably going to have like a dozen decimals, and carrying a dozen decimals is kind of a nuisance. So your problem 7, if you want to get started on it, the rodent population. The rodent population in a given city rose from 20,000 to 30,000 in 1 year. This 20,000 is going to be the p sub 0 in your formula. The 30,000 is the future population. That's the p of t, and your t is going to be 1 year. So into the formula that I saw flashed up on here for your problem, you're going to solve for the growth rate k by plugging in 30,000 for p sub 0 of t, 20,000 for p sub 0, and 1 in for t. And you're going to go like this. 30,000 in for p of t equals 20,000 in for p sub 0 times e to the k times 1, leaving k alone and plugging in 1 for t. You're going to do the algebra to solve that for k. On my problem, I'm going to plug in 1500 for the p of t. Then I'll follow it up with the equal sign. And for the p sub 0, I'm going to plug in 500. I'm going to leave the EE, I'm going to leave the KK, and I'm going to plug in 3 for the t. I'm going to solve this equation for k. I'm going to round k to 3 decimals. So I'm going to divide both sides by 500. That's going to give me 3 equals e. Instead of writing k times 3, I'm going to write e to the 3k power. Then I'm going to take the natural log of both sides. This is going to give me the natural log of 3 equals 3k times the natural log of e. We know the natural log of e is equal to 1, so this is really the natural log of 3 equals to 3k. And then I'm just going to divide both sides by 3 and get k, and I'm going to round to 3 decimals. So I do the natural log of 3 divided by 3. I'm going to write 0.366 for my k, just to round to 3 decimals. I don't want to write that many decimals down, and the more decimals you carry, the more accurate your answer is. So done with the first 2 sentences. That is not an answer to the question. The question is, how long will it take the population to reach 10,000? Well, what I'm going to do, I'm going to solve for t, because that's the how long. And into this formula for the left-hand side, I'm going to put 10,000 in for p of t, because p of t is the future population. I want the future population to be 10,000. For p sub 0, that's the starting population. The starting population snuck in that first sentence at 500. So for p sub 0, I'm going to plug in 500. And I'm also going to plug in 0.366 for k. I'm going to plug those numbers into the formula, and that's going to give me a formula that I could solve for t and get me to my answer. So into the formula, on the left-hand side, I plug 10,000. On the right-hand side, I plug 500 for p sub 0. I leave the EE. I plug in 0.366 for k. And I leave the TT, and I just need to solve for t. To solve for t, first I'm going to divide both sides by 500. And 10,000 divided by 500 is 20. So this gives me 20 equals e to the 0.366t. I'm going to take the natural log of both sides. This is going to give me the natural log of 20 equals 0.366t times the natural log of e. The natural log of e is equal to 1, so I can just cross it out. I'm going to divide both sides by 0.366. And I'm going to round my final answer to 2 decimals. Boy, this is inconsistent. Let me round it to 3 decimals. How about round my answer to 3 decimals, even though it doesn't say? Oh, on yours it does say. Yours says it rounds. Yours says round the final answer to 2 decimals. I'll round my final answer to 2 decimals. So let me put this in here. Round to 2 decimals. So there's 2 different numbers that we're getting in our computations. The first is a k. We'll round k to 3 decimals. I know I asked for that on the test. And our final answer, I'm going to round to 2 decimals. I get my final answer by going natural log of 20 divided by 0.366. And I'm going to write 8.19 because the number after the 8's a 5 tells me to round that up. I get 8.19 equals to t. And for my answer, the time is in hours, so it will take 8.19 hours for this bacteria population to grow from 500 to 10,000. And in my answer, I'd probably just write that, but I could write a sentence in 8.19 hours, the bacteria population will be 10,000. So flashing back to your broken up version of problem 7, you're going to do the math to solve for k. I think you're going to get k equal to 0.405. Assuming I haven't made a math error here, I did 30,000 divided by 20,000, and I did some math in my head. I think I did it right. So anyway, I think your k is 0.405. What you're going to do for your next part, this 100,000 is what your future populations needs to be. You're going to plug in 100,000 for your future population into this formula. Your starting population is going to be the 20,000, and that you're going to plug in for p sub 0. Assuming I have the right k, I didn't really do any algebra, I kind of did some algebra in my head, I guess. You'd plug that in for k, you'd plug those 3 numbers into the formula, and you'll solve for t, and you'll want to round your answer to 2 decimals. Nine and 10 are similar problems. So if I read this, the population of a city is expected to triple in 20 years. The city currently has 10,000 residents. How long will it take to get 50,000 residents? It gives me the same formula, tells me to round k to 3 decimals, and it tells me to round my final answer to 2 decimals. This short little question needs to be broken up into pieces. The first couple sentences I'll use to help me solve for k, and then I'll use the last sentence to help me get my answer. Similarly, my question number 10, the population of a certain city is expected to double in 20 years. The city currently has 1,000 residents. How long will it take to get 5,000 residents? If you lay my question 9 on top of your question 10, they're essentially exactly the same questions, except you have the word triple as opposed to double. We have slightly different numbers. Both of these problems, even though they're short sentences, need to be broken up. When you go to do your problem 9, the first thing you're going to do is take the first 2 sentences and help you get a value for k. So what you're going to do, you're going to plug in 20 for t. The city currently has 10,000 residents. You're going to plug in 10,000 for p sub 0. And you're going to triple that 10,000 and multiply that by 3 and get 30,000 for p of t. You're going to take these numbers, plug them into the formula, and you're going to solve for k and round to 3 decimals. Once you get done with that, you're going to answer the question. The question is, how long will the city take the city to get to 50,000 residents? That's going to go in for a PFT. That's the future population that we ultimately want to know how long it takes to get there. So we're going to plug in 50,000 for PFT. You will have just figured out what K is, and I know the P sub 0 is the starting population of 10,000. You're going to plug those 3 values into the formula, and you're going to solve for T. Ultimately, I want to answer the question, how long or how many years will it take the city to get to 50,000 residents, and I'm going to round to 2 decimals. My problem 10 is going to work exactly the same way as your problem 9. So the population of the city is expected to double in 20 years. The city currently has 1,000 residents. The 20 is going to go in for the T into my formula. The initial population of 1,000 is going to go in for my P sub 0. And my P of T, it's really P of 20 in this case because the T is 20. I'm going to double the 1,000 residents to 2,000 and put that in for P of T. I'm going to plug all these 3 numbers into the formula and solve for K. So I'm going to go P of T, 2,000, equals to P sub 0, 1,000, times E to the K times 20, plugging in 20 for the K. Now I'm going to divide both sides by 1,000. And this is going to give me 2 equals E, and I'm going to write that instead of K times 20 as 20K. I'm going to take the natural log of both sides and get the natural log of 2 equals 20K times the natural log of E. The natural log of E is equal to 1, so this really gives me the natural log of 2 equals to 20K. I'll divide both sides by 20. On the right-hand side, that's going to give me the K that I'm looking for. And on the left-hand side, I just do natural log of 2 divided by 20. And I get 0.0346. The 6 is going to bounce that 4 up to a 5. I'm going to write in 0.035 for my K. Now I'm going to move down to the second part. And in the second part, I have to use K equal to 0.035. I'm finding out when the city's going to have 5,000 residents. That's what the left-hand side is going to be. So my P of T side is going to be 5,000. And my city started off with 1,000 people. My P sub 0 is going to be 1,000. And I'm going to solve for how long. And how long means I'm solving for T. So I'm going to go 5,000 in for the left-hand side, the future population, equals 1,000, the starting population, times E to the 0.035 times T, and then just do my algebra. I'm going to divide both sides by 1,000. That's going to give me 5 equals E to the 0.035 T. Take the natural log of both sides. It gives me the natural log of 5 equals 0.035 T, natural log of E. Natural log of E is equal to 1. I divide both sides by 0.035. On the right-hand side, I get my T. On my left-hand side, I'm going to round to 2 decimals by going the natural log of 5 divided by 0.035. And I'm going to round that to 45.98. The 8's not going to round up because the number after it isn't big enough to force it to round up. And my time is in years because the city's going to double its population in 20 years. So for my answer, I'm going to write 45.98 years. And I could write a sentence saying it will take 45.98 years, about 46 years for the city to get to 5,000 residents. Just in case you need to see your problem 9 again. There it is. Problems 11, 12, 13, and 14 are the end of the section, so we only have a few problems left to go. And they're half-life problems. And in half-life problems, the growth rate needs to be negative. And these problems, just like the 4 problems that we just did, look deceptively short, but they're the 2-part problems. So it says, problem 11, the half-life of a certain element is 10 years. A 20-ounce sample of the element is obtained. How long will it take for there to be 12 ounces of the sample left? It gives me the formula. And what I'm going to need to do is I'm going to need to break that sentence or the question up into 2 pieces. The first 2 sentences and then the last sentence need to be separated. I'm going to use the formula and the numbers in the formula to get started. In the first part of the problem, I'm going to solve for K. And immediately, as I read through this, the half-life of a certain element is 10 years. That 10 is going to go in for T into my formula. And then it says a 20-ounce sample of the element is obtained. That's the starting amount. So in for my P sub 0, I'm going to plug 20 in for 20 ounces. And if 10 years is the half-life, then I know that in the future, in 10 years, I'm going to have half of the 20 left. The future amount I'm going to have in 10 years is half of my 20, which is 10 ounces. I'm going to plug these numbers into the formula. On the left-hand side, I'm going to put the future amount of material, which is half of the 20 ounces, which is 10 ounces. On the right-hand side, I'm going to put the starting amount, which is 20 ounces, the letter E, the letter K, and I'm going to plug in 10 for T, and I'm going to solve for K. So, and round to 3 decimals, K should be negative. If it doesn't come out negative, you've made a mistake. Because in order for the amounts to get smaller, you need negative growth. Once you get done with the first 2 sentences, we're going to move into the last sentence. We're going to solve for T. The question says how long. That means I'm solving for T. The 12 ounces here is the future amount. That's going to be the P of T. The starting amount is 20 ounces, so the P sub 0 is going to be 20. And the K for the formula is from the answer to part above. If you take these 3 numbers, 12 in for the left-hand side for the P of T, 20 in for the starting population, and K, being a negative number, in for the K, and solve for T, you'll get the answer to the question. I'll flash this back up just in case this isn't enough to get you going, but I'll start with my number 12. 12 tells me the half-life of a certain element is 100 years, so I know the time is 100 years. A 40-ounce sample of the element is obtained, so the initial amount of the element is 40 ounce. And then in 100 years, I'm going to have half of that 40 ounces left. My P of 100, or my future population after future amount, the future number of ounces, is going to be 20, because half of 40 is 20. I'm going to plug 20 in for the left-hand side, 40 in for the P sub 0. I'm going to leave the E alone, leave the K alone, and in for T, I'm going to plug 100. And I'm going to solve this for K and round K to 3 decimals. I'm going to divide both sides by 40. 20 divided by 40 is a half. It's going to be easier to use 0.5 on my calculator instead of 1/2. So I'm going to write this as 0.5 equals e to the 100k. I'll take the natural log of both sides. That's going to give me a natural log of 0.5 equals 100k times the natural log of e. The natural log is e is equal to 1. I'll divide both sides by 100. And I'm going to get a value for k, and I'm going to round it to 3 decimals. So I'm just going to do the natural log of 0.5 divided by 100. Should be negative. I get negative 0.0069. That 9 is going to round that 6 up to a 7. I'm going to write negative 0.007 for k. Actually, just graded the Chapter 6 test for my current semester's Math 151. This number came up exactly, 0.0069, which rounds to 0.007 negative on that test. All right, how long will it take 10 ounces of the sample to be left? So the 10 is the future population. That's going to go on the left-hand side. The starting amount, the 40, is going to go in for the p sub 0 still. It's still the same starting amount. And the k is going to be negative 0.007. And I'm going to solve for t. So into the left-hand side, I'm going to plug 10. Then I'm going to plug 40 for the p sub 0, negative 0.007 in for the k, and I'll solve for t. I'll divide both sides by 40. 10 over 40 is 1/4, which is 0.25. I don't need my calculator to do that, but you can use your calculator. So I get 0.25 equals e to the negative 0.007t. Take the natural log of both sides. I get the natural log of 0.25 equals negative 0.007t times the natural log of e. The natural log of e is equal to 1, so I don't need it. I divide both sides by negative 0.007. And I'm going to round to 2 decimals, and it's going to be my answer, and it's going to be in years. So I'll do the natural log of 0.25 divided by negative 0.007, and I get 198.04. And I'm going to just say 198.04 years for the answer to my question. The value for k doesn't need to be in my answer. I need k to get to the answer, but I don't need to use k in my answer. Basically, it's going to take 198 years for that 40 ounces to go down to 10 ounces. All right, let me flash number 11 up here just in case you couldn't get it done without me, giving you a good push. 13 and 14 are essentially the same questions with different numbers. So these are the long versions, and these are the broken up versions. So I'm going to give you the broken up version of problem 13, and heck, I'll do the broken up version of problem 13 and not do my problem 14. So pause the video, try to do problem 13, and then maybe just watch to see if you got it right. So I will do problem 13 for you real quickly here. So the half-life of an element is 5 years. That's the t is equal to 5. A 60-ounce sample is obtained. That's the initial amount. That's the p sub 0. The future amount, after 5 years, we're going to have half of that 60, and half of 60 is 30. I'm going to plug those numbers into the formula and solve for k. I'll get 30, the future amount, equals 60, the starting amount, times e to the k that I don't know, times t, which is 5. I'm going to divide both sides by 60. When I divide by 60, I get a half because it's a half-life. I'm going to write 0.5 equals, and on the right-hand side, I'm going to write 5k in the exponent. Take the natural log of both sides. Get the natural log of 0.5 equals 5k times the natural log of e. The natural log of e is equal to 1. I'll divide both sides by 5. The right side's going to give me the k. The left side's going to give me the natural log of 0.5 divided by 5. And I get negative 0.13. I'm going to round that to a 9 because the 6 in the fourth position rounds the 8 up to a 9. And the instructions say round k to 3 decimals, round your final answer to 2 decimals. Done with the first 2 sentences, moving on to the last sentence. In the last sentence, I need to use that negative 0.139 equal to k. And then, how long will it take till 15 ounces of the sample are left? The starting amount is 60 ounces. So the p sub 0 is still 60. And the left-hand side is going to be the 15 that I have left. So I'm going to plug 15 in for the left-hand side, 60 in for the p sub 0, negative 0.139 in for k, and I'm going to solve for t. I'll divide both sides by 60. I'll do 15 divided by 60, which I think is 0.25 on my calculator. So 15 divided by 60 is 0.25. Gives me 0.25 equals e to the negative 0.139t. I'll take the natural log of both sides. and get the natural log of 0.25 equals negative 0.139 t times the natural log of e. The natural log of e is equal to 1, so I can just cross it out, divide both sides by negative 0.139. The right-hand side is going to give me t. The left-hand side, when I do the natural log of 0.25 divided by negative 0.139, will give me the 9.97 time as in years, rounded to 2 decimal places. My answer to problem 13, it's going to take 9.97 years for there to be 15 ounces of the material left. So that's everything in this chapter that's test worthy. We do still have section 6.9 left, but I've never asked a question from section 6.9 on the test. The only reason you do 6.9 is if you want to use a note card on the test. All right, so I'll stop the video and